everyone, my name is Raina D. Jute and welcome to my Leetcode problem solving video for Module 12. This week I tried something new, so I got feedback from my father who works in tech, and he gave me advice on how to approach these problems in a way that's a bit more intuitive and less just trying to memorize code. So the technique I'm using is called problem decomposition. I didn't instantly know any of the optimal solutions for these problems. Instead, my thought process was, how do I take apart these problems? How do I think through them in plain English first, and then translate that into code? This process is about building a repeatable strategy for approaching unfamiliar problems, not memorizing solutions. So let's get into the first problem, which is binary search. So how I broke down this problem was, first, understanding that I'm given a sorted array and a target value. I need to find the index of that target or return -1 if it doesn't exist. So when I think about what this is really asking, I have data that's already ordered. I need to locate one specific item efficiently. The straightforward approach would be to scan through every element once, which would be O of n. But is that the best and most efficient way? So here's where I stop and think, what property can I exploit? So this array is sorted, that's intentional. If it wasn't sorted, the problem wouldn't matter as much. So then I ask myself, if the array is sorted, how do I naturally search it? Well, if I'm looking for something in a sorted list, I don't start at one end. I start in the middle. If the target is smaller than the middle, it's definitely on the left. If it's larger, it's definitely on the right. That eliminates half of the search space immediately. So that's the pattern that I chose here, which is divide and conquer. And it's powerful because I keep cutting the problem in half. So in plain English, step 1 is start with 2 pointers at the beginning and end. Step 2 is to pick the middle. Step 3 is to compare the target to the middle value. Step 4, if it matches, great, then we return the index. And step 5, if the target is smaller, then we search the left half. If the target is larger, then we search the right half. And then we keep going until the pointers cross or I find the target. This works because each step eliminates half of the remaining elements. So with 1,000,000 items, I'm done in about 20 steps. That's logarithmic time, which is O log n. It's fundamentally more efficient than scanning linearly one by one. This is a pattern I recognize as binary search, and once I see the pattern, I know there's a proven implementation that this works. Problem number 2 is search a 2D matrix. So as we can see in the example 1, we have a 2D matrix. Each row is sorted, and here's the key detail. The first element of each row is greater than the last element of the previous row. So 7 is less than 10, and then 23 is greater than 20. So that means this entire matrix is globally sorted. It's just arranged in a 2D grid instead of a 1D line. The task here is the same as before, so we determine if a target exists. When I see this, I think, wait, if the entire matrix is sorted globally, then technically it's the same as a sorted array. The fact that it's in a 2D grid is just a storage detail and less of a foundational shift in logic. So I ask myself, can I treat this like the previous problem? Can I apply a binary search? The only challenge with this one is that when I calculate a middle index in a 1D array, I need to convert it back to a 2D coordinate, but that's just math. So in plain English, first, we treat the 2D matrix as a flattened 1D sorted array, so indices 0 to m times n minus 1. Then we use a binary search on this imaginary 1D array. When I calculate mid, I convert it to a row and column coordinates. Then we compare the matrix row and column with the target. We adjust the search bounds like normal binary search. And this works because the matrix structure guarantees that when it's flattened, it's still sorted globally. So binary search applies directly. I'm not inventing anything new. I'm recognizing that this problem has the same structure as the previous one, just with a coordinate conversion step. This reinforces the pattern. Sometimes a problem that looks different is actually the same problem in disguise. So recognizing that saves a lot of time and a lot of effort. Problem number 3 is Coco eating bananas. Okay, so Coco has a pile of bananas. She has H amount of hours to eat all of them. Each hour, she chooses a pile and eats K amount of bananas from it. If a pile has fewer than K bananas, she eats the whole pile of that hour, then does nothing for the rest of that hour. I need to find the minimum eating speed, K, such that she finishes all the bananas within H hours. At first glance, this doesn't really look like a search problem at all, because where's the array to search? Where's the sorted data? But if we think about this a little bit differently, what am I really searching for? A speed or a threshold value? And here's the key insight. If Coco can finish at speed 100, she can definitely finish at speed 101. If she can't finish at speed 50, she can't finish at speed 49 either. So there is a boundary. Below it, she can't finish. Above it, she can. And I want the minimum speed that works. This is just a classic binary search pattern. So even though I'm not searching an array, I'm searching an answer space. So the approach here is, first, the minimum possible speed is 1, so eating 1 banana per hour. The maximum useful speed is the largest pile, so eats any pile in 1 hour. For each candidate speed, calculate how many hours she would need. If she finishes within H hours at this speed, try a slower speed, so we search lower. If she doesn't finish, try a faster speed, so we search higher. Then we keep narrowing it down until we find the minimum speed that works. Binary search works on any monotonic function. As the speed increases, time decreases. So there's always a threshold, and binary search finds it in O log max pile multiplied by n time. This was a moment where I had to recognize the pattern beneath the surface. So the problem description talks about bananas, but that's just fluff. The underlying structure is binary search on a threshold. Problem number 4 is longest substring without repeating characters. So decomposing this problem, I'm given a string. I need to find the longest continuous substring where none of the characters repeat. For example, in this one, ABC, ABC, BB, the substrings without repeating characters are A, AB, ABC, and BCA, CAB, B. The longest is ABC with a length of 3. My initial thought is that I could check every possible substring and see if it has repeating characters. But how many substrings are there? For a string of length n, there are n squared possible substrings. Checking each one is O of n, so that's O of n to the third, which is slow for really large inputs. But if we think about this a little bit differently, imagine we have a window that slides across the string. I expand the window by adding characters on the right. As I expand, I track which characters are in the window. If I encounter a character that's already inside, I have a duplicate. When that happens, I shrink the window from the left by removing the characters until the duplicate is gone. The window is always valid, it never contains repeats. As I slide this window across the entire string, I track the maximum size that it ever reaches. That's the answer, which in this case is 3. The key insight is both pointers move only forward, never back, so I visit each character roughly twice, giving me O of n time instead of O of n to the third. And then in plain English, we first use 2 pointers, left and right, starting at 0. Then we use a set or a hash map to track the characters that are currently in the window. Then we expand the window by moving the right and adding characters. When we find a duplicate, we shrink the window from the left until the duplicate is gone. Then we keep removing characters from the left in the set. After each step, we record the maximum window size that we have seen. And then we just return the maximum. This is the sliding window technique that we've seen in a couple of other problems. The power is in maintaining a valid state and sliding it across the problem. So instead of checking every possibility, we maintain one valid window and then we optimize as we go. I recognize this as a sliding window problem once I framed it that way. It's a pattern that applies to many substring and subarray problems. And then we have our final problem, which is subsets. So we're given an array, and I need to return all possible subsets. For 1 and 2, that's 0, 1, 2, 1, and 2. For 1 and 2 and 3, we end up getting 8 subsets. So if we think about the structure, for each element, we have 2 choices. We can either include it or exclude it. If I have n elements and I make 2 choices for each, that's 2 to the power of n total combinations. So I know that the output will be exponential in size. There's no way around that. So we have to generate 2 to the power of n subsets. But how do I systematically generate all of them? So there's actually 2 options here. The first option being backtracking. So we think of it as a decision tree. At each element, we branch into 2 paths. So we would start with an empty current subset. For each element, we make a decision, include it or don't. Include the element in the current subset and recursively process remaining elements. When I've made decisions for all of the elements, I have one complete subset, record it. Then we backtrack, we remove the element and try the other branch. And then we repeat until all branches are explored. This naturally generates all 2 to the power of n subsets because we explore every possible decision path, and that's the solution that we used here. Then there's option 2, which is iterative doubling. So with this one, we would start with a list containing just the empty subset. For each number in the array, we take all existing subsets in the list. For each subset, we create a copy and add this number to it. All these new subsets Then we add all these new subsets to my list, and then we continue until I've processed all the numbers. For example, if we have 1 and 2, then we start with an empty array. Then we process 1, we add 1 to it, so it's empty array and then 1. Then we process 2, and we add 2 to it, so it's empty array, 2, 1, and then 1 and 2. Then the results is 4. Both of these options work because they both generate all 2 to the power of n subsets. Backtracking is recursive and elegant, and it mirrors the decision structure naturally. Iterative doubling is bottom-up and intuitive, so you build the answer step by step. The time complexity for both is O2 to the power of n because the output itself is 2 to the power of n, so you can't do better than the size of your output. Backtracking is more suitable if you are comfortable with recursion and you want concise code. Iterative is great if you prefer a bottom-up logic and want to avoid recursion overhead. So both solutions are valid. The choice depends on the context and what feels natural to you. So this is a pattern I recognize as a combination generative problem, and once we frame it that way, I can choose the approach that best fits my thinking style. So to wrap up, this is what I've learned from these 5 Leetcode problems. I learned that the key to understanding the logic is decomposition. So before I code, I ask, what is this problem really asking? What structure does it have? Are there constraints that I can exploit? 3 of these problems use binary search, but they all look different. The pattern is the same, so monotonic functions, threshold boundaries. 1 uses a sliding window, maintaining a valid state and optimizing. 1 uses backtracking, exploring the decision tree. When I recognize a pattern, I know there are proven approaches. That's not cheating, it's learning from what other people have already discovered. So understanding that the pattern matters more than inventing a solution from scratch. The real skill that I'm working on is building a repeatable strategy. We decompose, think in plain English, identify the pattern, apply the approach, and then optimize if needed. That's how I approach problems that I've never seen before in a way that sticks with me enough that I can recognize patterns moving forward. So that's all I have for this video. Thank you for watching, and I will see you on the next one.